All right, in this section, we'll be looking at rational functions. And what makes it rational is that it's you can write it as a quotient of two polynomials. So in this case, we're looking at the toolkit functions of 1 over x and 1 over x squared. This goes into great detail about the behavior of the function. So, as x goes to positive infinity, as x goes to 0 from the positive side, you're going to go towards infinity. And then as x goes to infinity, the function is going to go towards 0. So each of these ends takes on a different behavior. So you can look at this slide and focus a little bit more on those. What's important is to note that the denominator dictates what the vertical asymptote will be. So in this case of our toolkit function, we don't want that to equal 0. So that means our asymptote is going to be at x equals 0. And then there are some rules coming up that help dictate whether or not there's a horizontal asymptote, where that is. So one of the rules says that if the degree of the numerator, I'm writing this like this a little bit later, if that's less than the degree of the denominator, then you've got a horizontal asymptote at y equals 0. The other rule says that if this is greater than the degree of the denominator by 1, then it's going to be what's called a slant asymptote, and we'll go into that a little bit greater in a few slides ahead. And then the other example is that when the degree of the numerator is equal to the degree of the denominator, you're going to get, it's going to go towards the ratio of the two leading coefficients. So we'll look at all those circumstances in the next coming slides. Here again is kind of a breakdown of what those end behaviors are. And this is an example when you're changing, it's shifting. This slide actually just wants you to use arrow notation, which is what this was, to describe what's happening in this situation. Don't worry about that. I don't think I even test you on that at all. But let's look at this one. So for this one, we've got our basic toolkit function of 1 over x. And then let's look at what's happening. We've done a lot of these transformations before. So let's just visually look at what the transformation is and write our equation based on that. So we're shifting. It would normally go through the origin. So it would go something like this and like this. So what has happened to the graph? It's shifted to the left 2. So that means we're going to end up with 1 over x plus 2. And then we've gone up 3 units. So we're going to add a 3 on the end here. Now let's go ahead and look at this in terms of the asymptotes. So we don't want x to equal 2. So that means that we're going to have a vertical asymptote at the point x equals 2, because our function is not identified at that point, which means as we approach it from the left and the right, it's going to start, it'll start approaching that number but never get to that number. So that's where our vertical asymptote is going to be. And then let's look at our horizontal asymptote. So what we want to do in this case, we can see it a little bit better if we turn this into a common denominator. So that's going to give us 3x plus 6 plus 1 all over x plus 2. And now you can see we have the same degree. So if you remember, when we have the same degree, when the degree of the numerator equals the degree of the denominator, we're going to have the ratio. So in this case, we have a 3 and a 1. And that's going to give us 3. So this will be our horizontal asymptote at y equals 3. So that's where that line is coming from. So one thing to note, your vertical asymptote, you're never going to cross. But there might be instances when you're going to cross your horizontal asymptote. So keep that in mind as you're graphing things. If you get a number that's below this line, go ahead and go with it. There's a chance that that's one of those special circumstances where it would actually cross that line. Here's another example of our function x plus 3 divided by x squared minus 9. So factor that out if possible. And because these factors are reducible, we end up with 1 over x minus 3. So we don't want x to equal 3, which means that our asymptote, our vertical asymptote, is going to be at x equals positive 3, which you can see here. And then in reduced form, you can see that the degree of the denominator is less than the degree of the numerator. So our other asymptote is going to be at y equals 0, which we have here. And this one gets pretty complex. So they've given us the equation, and we want to find the horizontal and vertical asymptotes. So to find the horizontal, let's look at the degree of the numerator and the denominator, and you can see they both are to the second power. So they're equal, which means we want to take the ratio of those coefficients. So don't, this is kind of a mixed up order than usual. So focus on just the coefficients for those values. So we've got a positive 2 here and a negative 1. So that's going to give us a negative 2. That's going to be our horizontal asymptote. So you can see that we've got that at y equals negative 2. And we determine that by comparing the degree of the numerator and the denominator. And now let's look at our vertical asymptotes. So we want to focus on this part right here. And we can rewrite that. So you can put negative x squared minus x plus 2. Let's pull out a negative 1. That's going to leave us with x squared plus x minus 2. And then let's factor this. So we need to come up with a negative 2 and a positive 1. So 2 and 1 is going to get us there, but we need a positive 2 and a negative 1. So that's going to give us x minus 1 times x plus 2. So our asymptotes are going to be at x equals 1 and negative 2. So now you can see here's our negative 2 asymptote and our negative 1 asymptote. And then most of this we're not having you graph, but if you needed to graph it, then you would just substitute some of these values in between, maybe help by finding your intercepts, however many you have, and look at the behavior of that function on that defined interval. So you would have this interval from here to here, this one from here to here, and this one in between the two. So you'd want to focus on what that function does within those intervals. Here's another example where we've got our function x squared minus 1 over x squared minus 2x minus 3. So if you'll notice right away, our degrees are equal. So that means we're going to take a ratio, and that ratio is just 1 over 1. So our asymptote is going to be at y equals 1. And our vertical asymptote, when we factor and reduce, we end up with the denominator of x minus 3. So we don't want x to equal 3, which means our vertical asymptote is at x equals 3. You can see that there. And then this removable discontinuity is an interesting thing. So what happens is you'll notice that we got rid of this factor. Well, if that factor, if x equaled negative 1, then that would make the denominator 0. We factored out, so it doesn't apply, but that still affects our graph. So we end up with this little hole right there at the x equals negative 1 value. And we won't go into this anymore in the class, but if you see that little open dot there, that's what this is talking about. Because we factored it out, it doesn't really apply so much. You may not even see it if you graph it using a graphing calculator or some other graphing utility, but know that it is there. And here's another example. So we've got our degrees. Once we reduce them, it ends up being 1 over x plus 2. So we encounter this all the time. So we know our horizontal asymptote is at y equals 0. So this is usually the case when we don't have a factor up here, when it kind of holds the toolkit function look. And then the next thing you want to do is look in the asymptote. So if x plus 2 is the denominator, then we don't want x to equal -2, which means that's our asymptote. So we've got an x equals -2 asymptote here. And then, again, because we eliminated this factor, we now have a removable discontinuity at the point x equals 2. So we're going to put our little open dot right there. Again, I don't think you're going to come across this in any of the homework, definitely not in the tests. So don't worry, don't focus too much on this. This one is also looking for the horizontal asymptotes. So we've got our function here, and when we factor it out, this one is only looking at the horizontal. So this is where we're looking at our degrees. So we've got a single x here and a squared x here. So our numerator, the degree of the numerator is less than the degree of the denominator. So we're going to get an asymptote at y equals 0. Here's another example. This is our function. And what you want to note here is that we have our vertical asymptote at x equals 1. So we can spot that without having to do too much calculating. And then what's tricky here is because the numerator degree is greater than the denominator degree by 1. That's the tricky part right there, is that it's greater than it by 1. Then that means we're going to have a slant asymptote. So you can see that slant right there. So what we want to do for that is actually take our, we want to do the division and find out our quotient. In this case, we can do the math if you want to, but we can also just skip it. Our quotient ends up being a 3x plus 1 with a remainder of 2. So we're only focused on this part. How many times did it go in whole? So it ends up being 3x plus 1. So you would graph your line, y equals 3x plus 1. Hopefully you remember how to do that. So we've got our intercept here. So we're going to have a dot at the plus 1. And then we're going, our slope is 3 over 1. So we're going to go up 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. Hopefully you're seeing that. And then you would just draw that line as your asymptote. So this is a slant asymptote. And that happens when the degree of the numerator is greater than the degree of the denominator by 1. And this one is showing you an example where they're equal again. So we're going to take the ratio of those coefficients. So we've got a 3 here and a 1 here. So it's just going to be 3. So our horizontal asymptote is at y equals 3, which you can see there. And then we'll focus on this denominator to find the vertical asymptotes. So once we factor those, we get x plus 5 times x minus 1. So we've got vertical asymptotes at x equals 1 and x equals -5. And again, when it comes to graphing these, just look at the behavior of that function between those intervals, and that can help you graph it. And this is a good example where, if they've graphed this properly for us, and this is an example where it actually goes below that horizontal asymptote, but again, it will never cross that vertical asymptote. This one, we're just looking at the vertical asymptotes. So they've already factored the equation for us. So you can see we've got vertical asymptotes at x equals +1, x equals -2, and x equals +5. And because our the degree of our numerator, this is going to be degree 2, because that's less than the degree of the denominator, which is going to be degree 3, our asymptote is at y equals 0. And this one, it zooms in a little bit more and it's focusing on the intercepts. So it's taking our last equation, this one right here, and it has found the intercepts for that and marked them. So you can see there's one here, and then we've got a y-intercept here. And then you can look at the function and determine its behavior on those intervals. I don't remember what this slide was for. I thought I had this marked off. Let's see. There you go. Yeah, we're pretty much done here. So this is, I'm not even sure what the slide was for, just looking at the toolkit functions one more time and the asymptotes for those, the basic toolkit functions. And then here was the very last one. So looking at one more equation, you can see this is the one where if you're starting to graph it, you can start looking at some of the degrees of the factors and focus on the shapes of the graphs from there. So here we have nothing. So we'll look at the behavior of the graph, the behavior of the function to determine the graph there. Here we were able to find the 2 intercepts, and then we can fill in the blanks from there based on the function and how it behaves within that interval. And again, here's one more intercept, so we can show how that function behaves over that interval. And that will be all for this section.